Before any of this gets strange, and it will get strange, it helps to sit for a moment inside a universe that felt completely sane. Picture it not as an abstract model, but as a room. 4 walls, a floor that doesn't shift, a ceiling at a fixed height. You know where the edges are. You know without checking that the distance between the far wall and your chair hasn't changed since you sat down. That's the room. And for 200 years, the best minds in physics were essentially working inside a room exactly like that, except the room was everything. Every galaxy, every grain of sand, every invisible corner of the dark between stars, all of it contained inside one vast unmoving stage. That was Newton's universe. Space as a container, not a participant, a container. Fixed, indifferent to what moved through it. The kind of space that exists whether or not anything is inside it. The kind that doesn't care what you're doing, that doesn't bend when you run or compress when something heavy passes through. It just sits there, holding things. That's all it does. Isaac Newton wrote this down in the Principia in 1687, though wrote down undersells it. He encoded it, built an entire mechanics of the world on the assumption that space was absolute, meaning it had a true real geometry that every observer shared equally, regardless of how fast they were moving or where they stood. There was no arguing with the walls of the room. The room was the room, and then there was time. Time for Newton was even simpler in a way. It flowed, uniformly, everywhere at once. A clock on this planet and a clock at the edge of the observable universe would tick together, beat for beat, without any drift between them. Not because they were synchronized, but because there was one time, one single river of it, and everything floated on the same current at the same speed. There was no version of time that moved faster in one place or slower in another. That idea would have been, well, it would have sounded like a fever dream to most physicists of the 17th century. It's worth pausing on how reasonable this all sounds, how intuitively correct. The floor you're lying on right now doesn't feel like it's negotiating its geometry with you. The hour that just passed felt, as far as your body could tell, identical to the hour before it. Newton wasn't guessing or simplifying. He was encoding what the universe appeared, with extraordinary consistency, to be doing. Every experiment confirmed it. Every calculation agreed with it. Planets moved exactly where they should. Tides came in. Cannonballs followed their arcs. The mathematics of absolute space and absolute time worked so well for so long that questioning them wasn't physics. It was philosophy. Maybe poetry. What this framework gave people, beyond accurate predictions, was something harder to name, a kind of solidity. The sense that if you could describe an object's position and velocity precisely enough, you could, in principle, trace every future state of the universe. The room had rules. The rules were stable. The rules applied to everyone. The heaviness of a thick textbook. That's the closest I can get to it. Not its weight exactly, more the specific resistance of it when you press your palm flat against the cover. That solidity, that sense that the object pushes back with a completely predictable force. That was Newtonian physics. The universe pushing back with a force you could measure, repeat, and trust. There was no reason to doubt the room. There was, however, and this is maybe where a small unease starts to gather at the edge of things, a problem with light. Not yet. That's the next conversation. But it's worth knowing, as you settle into this picture of an orderly, container-shaped cosmos, that light was already behaving in a way that didn't quite fit inside the room's walls. Nobody had quite admitted it yet. The mathematics still worked. The experiments were still being explained. The room felt solid. It would keep feeling solid for a while. Before we move forward, something I want to say. These videos are not put together casually. Every episode is research-backed, and the research notes for every single one of them are available on Patreon for anyone who wants to go deeper. This is a project that takes real effort, and if it has ever given you something, a moment of calm, a sense of wonder, something to think about, consider supporting it. And one more thing, if you have a teacher in your life, a friend who loves this kind of content, or children you want to grow up curious about the universe, you can gift them a Patreon membership. The link is in the description. Now into the next part. Sound needs something. That much was settled. Tap a tuning fork and hold it close. The vibration passes into the air and the air carries it forward, and somewhere a few meters away your eardrum catches it. Take the air away and the sound disappears. The medium is not optional. It is the mechanism. Waves need a medium. That was the understanding. And by the 19th century, light had been confirmed as a wave, interference patterns, diffraction, the whole set of behaviours that only waves produce. So the question followed naturally, almost boringly. What does light travel through? They called it the ether. Not a strange or mystical name at the time, just a word for a necessary thing. An invisible, weightless, perfectly elastic substance filling all of space, the medium through which light propagated just as sound propagated through air. It had to exist. Without it, the wave had nowhere to wave. The mathematics demanded a medium, so a medium was assumed. Physicists were not being reckless. They were being logical. The ether also solved a secondary problem neatly. It gave the universe an absolute reference frame. If light travelled through the ether at a fixed speed, then the ether itself was stationary, the one true background against which all motion could, in principle, be measured. Newton's absolute space given a physical face. All that remained was to detect it. In 1887, Albert Michelson and Edward Morley built an instrument in Cleveland, Ohio, designed to measure the difference in light's speed depending on which direction it was travelling relative to Earth's motion through the ether. The logic was clean. Earth moves through space. Space is filled with ether, so Earth must be moving through the ether. And if you measure light travelling in the direction of Earth's motion versus perpendicular to it, you should see a tiny but measurable difference. The way sound from an approaching source reaches you faster than sound from a receding one. The instrument was exquisitely sensitive, floated on a bed of liquid mercury to eliminate vibration, capable of detecting the shift they were looking for many times over. They found nothing, no difference, no shift. Light arrived at the same speed regardless of direction, regardless of Earth's motion, regardless of the season. They repeated the experiment as Earth moved to different positions in its orbit, eliminating the possibility they had just caught it at the wrong angle. Nothing. This is the part that's easy to misread as a non-event. A null result sounds like absence, like a clean slate. But it wasn't. The null result was a rupture, the kind that doesn't announce itself loudly, just sits there in the data, refusing to be explained away. The ether had to be there. Without it, the wave had no medium. Without it, there was no absolute frame. Without it, Newton's room lost its only candidate for a fixed background, and the experiment said nothing, said it clearly and repeatedly. Some physicists tried to save the ether. Lorentz proposed that objects physically contracted in the direction of motion through the ether, coincidentally masking the expected shift. Fitzgerald proposed the same independently. The math worked out. The explanation was internally consistent. But something about it, something about needing the universe to hide its own structure so precisely, to arrange a cover story so exact, felt like the wrong kind of answer, like a picture hung slightly crooked that everyone keeps rehanging instead of checking whether the nail is in the right wall. The ether survived another 18 years, patched and propped until 1905. Not because anyone had proved it existed, because nobody had yet found the cleaner answer. The cleaner answer did not involve saving the medium. It involved questioning the assumption underneath the assumption, the one so embedded in the logic that it had never quite been named as an assumption at all. Light did not behave like sound. Maybe it never had. Maybe the question, what does light travel through, was the wrong question. Not unanswerable. Wrong. Built on a premise the universe simply did not share. What that meant for the room, for Newton's fixed stage, for the comfortable certainty that space and time were stable and separate and sane, That was still a few pages away. The paper was 26 pages, written in 3 weeks apparently, though that detail might be mythology by now, the kind that attaches itself to origin stories. What matters is what was in it, specifically near the beginning. 2 statements, not derived from experiment, not pulled from data, stated as postulates, meaning, assume these are true and see what follows. The first, the laws of physics are the same in every inertial frame of reference. The second, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the source. That's it. 2 sentences. The rest of the paper is consequence. It's worth sitting with the first one for a moment before moving on. An inertial frame is just a frame of reference moving at constant velocity, not accelerating, not spinning. You on a train moving smoothly, you standing still on a platform. The claim is that no physics experiment conducted inside either frame will produce a different result. There is no experiment that reveals absolute motion. You cannot tell from inside a closed box whether you are moving or stationary. Motion is relative, always, only ever relative. This is not new with Einstein, actually. Galileo had said something close. Newton's mechanics already obeyed it. What Einstein did was extend it, not just to mechanics, but to everything. Electromagnetism included, light included. And that's where the second postulate arrives, and where things get uncomfortable. If the laws of electromagnetism are the same in every inertial frame, and if those laws predict that light travels at a fixed speed, roughly 299,792,458 meters per second, then light must travel at that speed in every inertial frame, for every observer, whether they are stationary or moving toward the source or moving away from it. The number doesn't change. Press 2 fingers against a tabletop. Feel it hold. The table doesn't negotiate with your fingers. It doesn't give more resistance because you pushed harder or less because you're tired. It just holds. That's a rough version of what the speed of light does. It holds. It does not add your velocity to itself. It does not subtract it. Whatever you are doing, however fast you are moving, the light in front of you is pulling away at exactly the same rate as the light behind you is receding. Which is, and I want to be careful here, because impossible is a word that tends to close thinking rather than open it, which is deeply structurally strange. Because if light moves at the same speed for everyone, and 2 observers are moving at different speeds relative to each other, then something else must be giving. The numbers have to balance somehow, and the only things left to give, the only variables still in the equation, are space and time, distance, duration, the measurements that Newton had declared absolute. Postulate 1 plus postulate 2, taken together, make absolute space and absolute time mathematically untenable, not philosophically uncomfortable, not aesthetically unpleasant, untenable. The logic runs straight from those 2 sentences to the conclusion that different observers, moving at different speeds, genuinely measure different distances between the same 2 points and different durations between the same 2 events. This was not what Einstein set out to destroy. I don't think he set out to destroy anything exactly. He set out to resolve a contradiction, the one between Newtonian mechanics and electromagnetism that had been quietly accumulating since Maxwell wrote down his equations in the 1860s. The 2 postulates resolved it, cleanly, completely. The cost was the room. Newton's fixed, stable, universal stage, the one where space held its shape and time kept its pace, could not survive both postulates being true. And both postulates, as far as anyone has ever been able to test, are true. 2 sentences, the rest was consequence. Hermann Minkowski was 44 years old when he gave the lecture. September 1908, Cologne. A conference of German natural scientists and physicians. The room would have had that particular quality of large formal spaces. Sound arriving slightly late, the sense that words need to travel a small distance before they land. He stood up and told the audience that everything they thought they understood about space and time was about to become a shadow. Not a metaphor, as it turned out. Almost literally. He had been Einstein's mathematics teacher in Zurich years earlier. Einstein, by most accounts, was not a model student in Minkowski's classes, attended irregularly, submitted work that suggested ability without demonstrating effort. Minkowski reportedly found him talented in the way that occasionally frustrating students are talented. You can see the capability sitting there, slightly out of reach, not quite bothering to arrive. When the 1905 paper on special relativity appeared, Minkowski read it carefully. Then he did something Einstein had not done. He looked at the geometry underneath it. Einstein's paper had produced the right results through physical reasoning. Postulates, thought experiments, consequences carefully drawn out. But Minkowski saw that if you took the mathematics of special relativity seriously, as mathematics, it was describing something with a specific shape, not a shape in 3 dimensions. 3 dimensions of space plus time, but not time as a separate river running alongside space. Time woven into the same structure, a single 4-dimensional fabric in which every location needed 4 numbers to specify where and when. He called it Spacetime. The word is so common now that it lands without weight. It shouldn't. What Minkowski had noticed, and what the Cologne lecture tried to lay out, in mathematics that apparently left portions of the audience slightly adrift, was that you could not meaningfully separate space from time in a way that all observers would agree on. An observer moving at a different speed would slice the 4-dimensional block differently. What one observer measured as purely spatial distance, another would measure as a mixture of space and time. What one called duration, another would find distributed across both. The individual measurements were frame-dependent, but the combined 4-dimensional interval, the space-time distance, so to speak, that was invariant. That held. This is the part worth pausing on. Minkowski introduced the world line, the path an object traces through 4-dimensional space-time just by existing, not a path through space-time. Sit completely still and you are still moving through time, still drawing a line through the 4-dimensional structure. Move through space quickly and your world line tilts. The geometry of the tilt encodes how time and space trade against each other for different observers. He introduced the light cone, the surface in time that light traces out from any given event, dividing everything into what can be causally connected and what cannot. The past, the future, and, between them, a region that no signal at light speed or below can ever bridge. Space-like, time-like, words that only make sense once you accept that space and time are components of the same thing. Einstein's initial response to all of this was, by his own later admission, something close to dismissal. He called it, and there is some affection in the phrasing, even if it wasn't meant that way, superfluous erudition. Unnecessary mathematical elegance wrapped around physics that already worked. The postulates had given the right answers. The 4-dimensional geometry felt to Einstein in 1908 like decoration. Minkowski died in January 1909, an appendicitis at 44. He did not live to see what happened next, because by 1912 Einstein had changed his mind, fully, and with something that reads in his letters like genuine debt acknowledged. When he began trying to extend special relativity to include gravity, what would become general relativity, he found that the framework he needed, the mathematical language capable of describing curved spacetime, was precisely the language Minkowski had been building. The 4-dimensional structure wasn't decoration, it was the foundation. Without it, general relativity might have taken another decade, maybe more. That's speculation, but it's not empty speculation. Einstein himself said that Minkowski's work made the path significantly shorter. The lecture in Cologne lasted about an hour. The room was full, sound arriving slightly late the way it does in large formal spaces. Minkowski stood at the front and said that henceforth, space by itself and time by itself were doomed to fade into shadows, and only a kind of union of the two would preserve an independent reality. He was right. He died 5 months later, before most people had finished deciding whether to believe him. Lie still for a moment. Not metaphorically, actually consider it. Body horizontal, room dark, nothing moving. You might assume in that stillness that you have stepped outside of physics somehow. That physics is for things in motion, things colliding, things with measurable velocity. That stillness is a kind of pause. It isn't. You're doing something extremely specific right now. You're existing at a location, at a time. And that combination, location plus time, is what physics calls an event, not an occurrence, not something dramatic. An event, in the language of modern physics, is simply a point in space-time, a where and a when fused into a single specification. The chair you sat in this morning at 7:43, that's an event. The precise position of a photon as it crosses a room, that's an event. You lying still right now at this exact moment, that's an event. Unremarkable by ordinary standards, precisely defined by physics. This is a shift worth taking slowly. For most of human history and for all of Newtonian physics, the fundamental unit of reality was the object. A thing that persists. A thing that moves through space while time flows past it independently. The object and time were separate. The object had a location in space. Time told you when it was there. Two different quantities, one describing position, one describing moment. What the space-time picture does, quietly, without drama, is dissolve that separation. The object is not moving through space while time flows past it. The object is tracing a path through space-time. Every moment of its existence is a different event, a different point in the four-dimensional structure. The collection of all those events strung together is called a world line. Your world line started when you did. It has been accumulating ever since. Even now, lying still, not moving through space by any measurable amount, you are moving through time, which means your world line is extending. The line is being drawn whether you are aware of it or not. Stillness in space is not stillness in space-time. Stillness in space-time isn't possible. To exist is to trace a line through it. Think of it like, and this is the only comparison I'll reach for, and even then imperfectly, think of it like a thread being pulled slowly through fabric. The thread doesn't choose to move. It moves because the fabric is structured that way. Except in this case you are the thread, and the fabric is four-dimensional, and the pulling is just time passing. That's where it starts to feel strange. Because if your world line already exists, if every point along it is a specific pinned event in space-time, then what exactly is now? Not philosophically, physically. The event that is you right now is one point on a line. The event that is you 5 minutes from now is another point on the same line. Both events are part of the structure. Both have coordinates. Both are real in the same geometric sense. The sensation of moving through time, the feeling that now is special, that now is where you are while past and future are somewhere else. Space-time doesn't have an obvious place for that feeling. It describes the line. It doesn't describe the experience of travelling along it. Maybe that distinction matters. Maybe it doesn't. I'm not certain it's a question physics can fully answer or fully wants to. What it can say is this: the word object is almost a convenience. A shorthand for a world line we've decided to follow for a while. The coffee cup on the counter isn't a thing sitting in space. It's a dense, tight bundle of atomic world lines, all moving together through space-time, all accumulating events at roughly the same coordinates. When the cup breaks, the world lines diverge. When you fall asleep, yours continues. Quietly, without asking permission, without any of the drama the word space-time might suggest, it continues. Two people walk into the same room from different doors. One enters from the north, one from the east. They both see the same room, same walls, same objects, same light, but the proportions look different from where they stand. The north entry person sees more of the left wall. The east entry person sees more of the back. If you ask them separately to describe the room's shape, the descriptions would diverge in small but consistent ways. Neither is wrong. They are simply standing in different places, looking along different lines of sight. Now ask them both to measure the diagonal of the room, the true distance from one corner to the opposite corner, cutting through the air at an angle. That number, the actual distance, will be identical for both of them. The corner-to-corner measurement doesn't care which door you came through. That is roughly, very roughly, and the roughness matters, what the space-time interval does. Two observers moving at different velocities relative to each other will, when measuring the separation between the same two events, disagree. Not because of error, not because of imprecision, because space-time genuinely presents itself differently depending on how you are moving through it. One observer measures more time between the events and less space. Another measures less time and more space. The individual components shift, trade against each other, redistribute themselves according to the relative motion between observers. And yet there is a specific combination of those measurements, a particular way of mixing the time component and the space components together that produces the same number for every observer, regardless of their velocity. That number is the space-time interval. It is invariant, fixed, the corner-to-corner measurement that survives the different doorways. The formula, if you want to hold it without calculating it, works like this. Take the time between two events, scale it by the speed of light, square it, then subtract the squared spatial distances in each of the three directions. What remains is the interval. The subtraction is the strange part, not addition, as you might expect if you were simply combining components. Subtraction. Time and space don't add together to make space-time the way ingredients add together to make a mixture. They combine with a tension between them, a structural opposition built into the geometry, and what survives that tension is the interval. It's worth asking what it means that this exists at all. Nature did not have to work this way. A universe could, in principle, have no invariance. A universe where every measurement depended entirely on the observer's state of motion, where nothing held across frames, where the universe looked genuinely different and irreconcilably so from every vantage point. That universe would be almost impossible to do physics in. Patterns would be local accidents, not structural truths. The fact that the space-time interval holds, that beneath the disagreements about duration and distance there is a quantity that everyone agrees on, suggests that space-time has a real geometry, that the four-dimensional structure is not merely a convenient way of organizing data, but something with actual shape. The interval is the shape's signature, the proof that the geometry is there, which leads somewhere slightly uncomfortable if you follow it carefully. The interval being invariant means that space alone and time alone are, in a precise technical sense, incomplete descriptions of reality. Neither one, taken by itself, is a frame-independent fact. They are projections, the way the East Entry person's description of the room's left wall is a projection, real but partial, dependent on the doorway. The complete description lives in 4 dimensions. The interval is what you get when you stop projecting and measure the diagonal. Most of the time, this doesn't matter. At the speeds of ordinary life, the relativistic corrections are so small that space and time appear perfectly separate and stable, and Newton's framework works without detectable error. The interval is there beneath everything, holding, but nothing in daily experience forces you to notice it. It starts to matter near the speed of light. It starts to matter near extreme gravity. It starts to matter, in ways that are less obvious but perhaps more unsettling, the moment you ask what the interval actually is. Not how to calculate it, what it is. A quantity without an observer, a measurement that holds when nothing else does. Whether that makes space-time more real than space or time individually, or whether it simply means we have found a better description of the same underlying thing, that question stays open, honestly, and I'm not sure it has a clean answer yet. Put yourself on a train platform. Night, say, though it doesn't matter. The light conditions are just easier to picture in the dark. The train passes through at speed, long enough that both ends of it are visible for a moment. Now imagine 2 lightning bolts strike simultaneously, one at the front of the train, one at the rear. You are standing exactly at the midpoint between the 2 strikes. The light from both reaches you at the same instant. You conclude reasonably that the strikes were simultaneous. They happened at the same time. On the train, someone is sitting at the exact midpoint of the carriages. They are moving towards the point where the front strike occurred, and away from the point where the rear strike occurred. The light from the front reaches them first. They conclude, equally reasonably from equal evidence, that the front strike happened before the rear strike. Neither person is wrong. Neither is suffering from signal delay or a faulty clock or a trick of perception. The light is behaving exactly as it should. The measurements are clean. The disagreement is not an error. It is a structural feature of space-time. This is the train and platform thought experiment, and it has appeared in physics education for over a century, which means there is a risk it slides past without landing. So it's worth staying with the actual claim for a moment, not the setup. The claim: two observers in relative motion, measuring the temporal relationship between the same two events, can reach genuinely different and irreconcilable conclusions about whether those events were simultaneous, whether they happened at the same time, whether there was any time between them at all. The word simultaneous turns out to be frame-dependent. Like position, like velocity, it is a measurement that depends on the measurer's state of motion. There is no view from nowhere that resolves the disagreement. There is no third observer who can check and confirm which version is correct, because any third observer occupies their own frame and produces their own answer. What makes this different from ordinary disagreements is the absence of any underlying fact to appeal to. When two people describe a room differently, the room has a definite shape and the disagreement is a matter of perspective. When two observers disagree about simultaneity, there is no fact of the matter they are both approximating. The disagreement is not about the same underlying reality viewed from two angles. The disagreement is the reality. And here is where it quietly gets uncomfortable. If simultaneity is frame-dependent, if at the same time means different things to different observers, then now is also frame-dependent. The present moment is not a universal slice through the universe, clean and shared by everyone. It is local, personal. The set of events that are happening right now, according to you, is not the same set of events that are happening right now according to someone moving past you at speed. Two people passing each other on a street carry different nows, different collections of distant events that they would each call simultaneous with this moment. And the faster the relative motion, the more their present slices through space-time diverge. At ordinary speeds, the difference is immeasurably small. At relativistic speeds, it becomes substantial. At the speeds of distant galaxies receding from us, the divergence is, well, large. I want to be careful here. This is not a statement about perception, not about the time it takes light to carry information, the events that are now for a given observer, the theoretical set of everything simultaneous with this moment. That set is determined by the geometry of space-time, not by how quickly signals travel. The signals are irrelevant. It is the structure itself, which means the universe does not have a present tense, not globally, not in any frame-independent sense. Every now is somebody's now, attached to a particular motion, a particular world line, a particular slice through the four-dimensional block. Whether that means the past is still real somewhere, that the future already exists in some geometric sense, those implications are sitting just ahead. They follow from this the way cold follows from altitude, not dramatically, just inevitably. The platform is empty, the train has passed. Both lightning strikes still happened, and they happened in a different order depending on where you are standing. A clock ticks in a quiet room. You can hear it if the room is still enough, not loudly, just steadily, the way certain sounds become audible only when everything else stops. That tick is marking something real, a duration, a quantity of elapsed time that exists independently of whether anyone is listening for it. Now move the clock, not fast enough to notice. Walk across the room holding it, set it on a different shelf. The effect is there. The moving clock has ticked fractionally slower than one left stationary, but fractionally here means something so far below measurement that no instrument built by human hands could catch it. The physics is operating. The difference is genuine. It is simply at walking pace too small to see. This is time dilation, not a trick of perception, not a consequence of signals taking longer to arrive, not an artifact of the measurement process. A moving clock genuinely runs slow relative to a stationary one by a factor that depends precisely and only on how fast it is moving. Both clocks are working perfectly. Both are measuring real elapsed time. They simply measure different amounts of it between the same two events because they are moving differently through space-time. The factor that governs this, the Lorentz factor, usually written as gamma, behaves in a specific way. At low speeds it sits just above 1. The correction is real but negligible. A commercial aircraft travelling at cruising speed accumulates a time dilation effect of roughly a few nanoseconds per hour relative to the ground. The clock on the plane runs slow. The difference is measurable with atomic clocks sensitive enough to catch it, and it has been measured, and it matches the prediction without detectable error. As speed increases, gamma climbs. Not linearly, it accelerates. At half the speed of light, a moving clock runs about 15% slower than a stationary one. At 90% of light speed, it runs at roughly 44% of the stationary rate. At 99%, the moving clock is running at about 14% of normal. The closer you push toward the speed of light, the more severely time stretches, the more the moving clock falls behind, and the relationship between speed and this stretching grows increasingly steep. At the speed of light itself, gamma would reach infinity. Time for a massless particle travelling at light speed does not pass at all. A photon, if it experienced anything, would find no duration between its emission and its absorption. The journey takes no time. From the photon's perspective, if that phrase means anything, beginning and end are the same moment. This is not a metaphor. It is what the mathematics says, and the mathematics has been confirmed. The thing worth holding on to, the thing that distinguishes time dilation from simple perceptual difference, is that the clocks do not resynchronize when they come back together. If a clock travels away at speed and returns, it has genuinely accumulated less time than the one that stayed. The hands show different positions. The difference is permanent. There is no correction to apply, no illusion to resolve. Both clocks were right the entire time. They were just right about different things, which leads, inevitably, to the twins. The thought experiment is old enough to have worn grooves in physics pedagogy, but it still does what it was designed to do. Two people, identical twins, begin at the same age at the same location. One stays, one travels, at a significant fraction of light speed to somewhere distant and back. When the traveller returns, they are younger, not subjectively younger, not feeling younger, biologically, measurably, actually younger. Fewer heartbeats have occurred, fewer cell divisions, fewer seconds have passed in the traveller's body than in the body of the one who stayed. They are the same age at the start, they are different ages at the end. The universe accumulated different amounts of time for each of them, and neither was wrong to experience what they experienced. The resolution of why the asymmetry exists, why it isn't mutual, why the traveller ages less rather than each aging less relative to the other, involves acceleration, and that's a conversation for a different chapter. What matters here is the raw fact. Two people, same universe, different amounts of elapsed time. I find myself wanting to say something further about what that means, and then not quite finding the words that don't overreach. It means something about the nature of time that is still, in some ways, being absorbed. Not just by the public, by physicists. The implications settle slowly. The clock in the quiet room keeps ticking, steadily, marking something real, just not the same something for everything. Time dilation gets most of the attention, probably because time feels personal. The idea that a clock runs differently depending on how it moves touches something about experience, about aging, about what it means to move through a life. Space feels less personal. Distances seem like facts about the world rather than facts about observers. They are not. An object in motion is shorter along its direction of travel, as measured by a stationary observer, than the same object measured at rest. This is length contraction. It is not a compression of the object in any mechanical sense. The atoms are not being squeezed together. The object does not feel different from the inside. It is a geometric consequence of the same space-time structure that produces time dilation. The two effects are not separate phenomena that happen to coexist. They are the same phenomenon seen from different angles, one temporal, one spatial. Consider a long rod at rest. You measure it. It has a definite length. Now accelerate it to a significant fraction of light speed, moving along its own axis, and measure again. The measurement is shorter, not slightly shorter by the Lorentz factor, the same factor that governs time dilation. At 90% of light speed, a rod that measures 1 meter at rest would measure roughly 44 centimeters to a stationary observer. At 99%, roughly 14 centimeters, the same scaling, the same curve, the same gamma. This is not coincidence. It is the space-time interval enforcing itself. The interval, say, that combination of temporal and spatial separation that remains invariant across frames, is preserved precisely because time dilation and length contraction work in tandem. When a moving observer's clock runs slow, gaining time relative to the stationary frame, the spatial measurement shrinks to compensate. The two adjustments are not independent corrections applied by the universe to keep things tidy. They are two projections of the same four-dimensional geometry onto the three-dimensional measurements of observers moving differently through it. Think of it this way, and this is the only analogy worth reaching for here. A shadow cast by a vertical pole will change length depending on the angle of the light. The pole itself does not change. What changes is the relationship between the pole's true extent and the surface it projects onto. Different angles produce different shadow lengths. The pole's actual length, measured directly along its own axis, is invariant. The space-time interval is the pole, time and space separately are the shadows. They change depending on the frame. The interval does not. What makes length contraction slightly harder to absorb than time dilation is that it is purely relational. The rod is shorter for the stationary observer. From the rod's own frame, from the perspective of something moving with the rod is exactly its rest length. It is the stationary observer's ruler that appears contracted. Both measurements are correct. Neither represents a deeper truth about the rod's real length. The real length, in a frame-independent sense, is encoded in the space-time interval, not in either observer's spatial measurement. This is where the temptation arises to ask which observer is right, the stationary one who sees the contracted rod, or the moving one who sees the full length. The question has a clean answer and an uncomfortable one, and they are the same answer. Both are right, and neither measurement is more fundamental than the other. There is no view from outside space-time that resolves the disagreement in favor of one frame. There is only the interval, holding beneath both measurements, invariant and inaccessible to direct observation. A rod at rest has a length. Move it and its measured length contracts. Slow it back down and the length returns. Nothing about the rod changed. What changed was the geometry of the path it traced through space-time and the relationship between that path and the measuring frame. The rod was always the same rod. The measurement was always a projection. That's roughly where length contraction leaves you, back at the object unchanged, sitting inside a geometry that distributes its properties differently depending on who is looking and how fast they are moving. Not a trick, not an illusion, just space-time doing what space-time does. High in the atmosphere, about 15 kilometers above the ground, cosmic rays and protons mostly, moving at close to light speed, collide with the nuclei of air molecules. The collisions are violent in the way that things moving at nearly the speed of light tend to be violent, which is to say completely and without warning. Among the debris produced in these collisions are particles called muons. A muon is not exotic exactly. It behaves like an electron in most respects, same charge, same spin, but it is about 200 times heavier and it is unstable. Left alone, a muon decays. The average time before it does so, measured in a laboratory with the muon at rest, is about 2.2 microseconds, 2 millionths of a second. After that, statistically speaking, it is gone, converted into an electron and two neutrinos, the neutrinos carrying most of the energy away invisibly. Now do the arithmetic that the classical picture demands. A muon moving at roughly 0.994 times the speed of light covers about 660 meters per microsecond. In 2.2 microseconds, it travels something like 1.4 kilometers before decaying. The atmosphere is 15 kilometers deep. A muon created at the top of it should, by every expectation of pre-relativistic physics, decay roughly 10 kilometers before reaching the ground. The vast majority should not arrive. Ground-level detectors should find almost none. They find a great many. Muons are, in fact, the dominant component of cosmic radiation at sea level. They pass through you, through everyone, constantly, day and night, at a rate of roughly 1 per square centimetre per minute. The ground is full of particles that should not be there. This is the point where time dilation stops being a thought experiment. The muon carries a clock, not a metaphorical one. Its decay rate is a precise, measurable physical process, the same kind of process that ticks inside every unstable particle. That clock runs at a specific rate when the muon is at rest. When the muon moves at 0.994 c, the Lorentz factor for that speed is approximately 9.1, which means the muon's internal clock, from the perspective of a ground-based observer, runs at roughly 1/9 its rest rate. The 2.2 microsecond lifetime stretches to about 20 microseconds. In 20 microseconds at 0.994 c, the muon covers just over 6 kilometers, still not quite 15, but close enough that a distribution of muons with varying energies, some faster, some slightly slower, produces exactly the sea level flux that detectors measure. The numbers come out, precisely, consistently, every time. Bruno Rossi and David Hall confirmed this in 1941, measuring the distribution of muons at different altitudes and correlating it with their measured energies. The higher the energy, the faster the muon and the greater the apparent lifetime extension. The relationship followed the Lorentz factor without deviation, not approximately, not roughly, without detectable deviation. And then in 1966 at CERN, the experiment was run in reverse. Muons produced in a particle accelerator were bent by magnets into a circular storage ring, travelling at 99.7% of the speed of light. The Lorentz factor at that speed is about 12. The observed lifetime of those muons was 12 times the rest lifetime. The prediction and the measurement agreed to within experimental error. 12-fold. A muon that should have lasted 2.2 microseconds lasted closer to 26. Not because anything interfered with its decay, because it was moving fast enough through spacetime that time itself for that muon was passing at a different rate than for the laboratory around it. The muon doesn't know it's proving anything. It's just decaying at the rate it decays, in its own frame, on its own schedule, ticking down its 2.2 microseconds as faithfully as it always does. It is the geometry of space-time and the fact that the muon is tracing a different path through it than the detector waiting on the ground that produces the discrepancy. Is it strange that something so abstract, a geometric property of the four-dimensional fabric of the universe, shows up this concretely in this particular particle, falling through this particular atmosphere, landing in this particular detector? Maybe. Or maybe that's just what physics is. Abstract structure made visible in specific, measurable, unrepeatable, except that it always repeats detail. The muons keep coming. Right now, one is probably passing through the ceiling above you. It left the upper atmosphere longer ago than it should have, and it arrived anyway. At some point today or yesterday or sometime in the recent past, you have probably glanced at a map on a phone. A blue dot appeared roughly where you were standing. You trusted it. Maybe you followed it. Maybe you just confirmed your orientation and put the phone away. The whole interaction lasted a few seconds and produced no particular feeling of wonder. That blue dot is produced in part by general relativity, not as a background consideration, not as a minor footnote in the engineering, as a correction that must be applied continuously every day, or the system drifts into uselessness within hours. Here is the basic structure of GPS. A constellation of satellites orbits Earth at an altitude of roughly 20,000 kilometers, each carrying an atomic clock accurate to within a nanosecond. Your phone receives signals from several of these satellites simultaneously, compares the arrival times of those signals, and calculates its position by triangulation. The accuracy of that position depends entirely on the accuracy of the timestamps. A timing error of 1 microsecond, 1 millionth of a second, translates to a positional error of roughly 300 meters. Now introduce spacetime. The satellites are moving at approximately 14,000 kilometers per hour relative to the ground. Special relativity says that moving clocks run slow. At that speed, the Lorentz factor is small, but not negligible. The satellite clocks lose about 7 microseconds per day relative to clocks on the ground. 7 microseconds. If left uncorrected, this would introduce a positional error of a little over 2 kilometers per day growing. But the satellites are also sitting 20,000 kilometers up, where Earth's gravitational field is significantly weaker than at the surface. General relativity says that clocks in weaker gravitational fields run fast, because as space-time is less curved there, and less curvature means less time dilation. At GPS altitude, this effect causes the satellite clocks to gain approximately 45 microseconds per day relative to ground clocks. 2 effects, opposite directions, different magnitudes. The net result is that GPS satellite clocks run fast by roughly 38 microseconds per day, relative to clocks on the surface, 38 microseconds. That sounds negligible, and it would be, in most contexts, in a system where a single microsecond of error produces 300 meters of positional drift. 38 microseconds per day produces roughly 11 kilometers of error per day. Left uncorrected, a GPS system designed without relativistic corrections would be completely unreliable for navigation within the first hour of operation. The engineers who designed GPS knew this. They accounted for it before launch. The onboard clocks were deliberately tuned to tick at a slightly different rate on the ground, so that once in orbit, under the combined influence of velocity-based slowing and gravity-based speeding, they would settle to the correct rate relative to ground stations. The correction is not applied after the fact, it is built into the hardware. This is the part I find genuinely difficult to overstate, and I want to be careful not to, because overstating it would make it sound more dramatic than it actually is, and the point is precisely that it isn't dramatic. The point is that it's infrastructure. The relativistic correction in GPS is as routine as accounting for temperature in precise measurement, as ordinary as adjusting for air resistance in ballistics. The engineers did not find it philosophically troubling. They found it necessary. They built it in. They moved on. Space-time physics is not running in the background of the GPS system the way a theme runs in the background of a film. It is load-bearing. Remove it and the structure fails, which means, and this is the thing that took me a moment to fully absorb the first time I encountered it, every time a delivery van finds a street, every time an aircraft confirms its position, every time a phone tells you to turn left in 200 meters, the calculation depends on the fact that time runs differently at different altitudes and different speeds. Einstein's 1905 and 1915 papers are not historical artifacts. They are live engineering documents. The blue dot on the map is a measurement, a consequence of signals, clocks, geometry, and the specific way space-time curves near a mass. It is as far from abstract as physics gets, and it appears on the screen without any of this being visible, without any of it being felt. Just a dot, approximately where you are standing, accurate to a few meters, space-time quietly doing its work. The floor is pushing up against you right now. Not metaphorically, the surface beneath you, whatever it is exerting an upward force on your body equal to your weight. You don't feel it as a push because you have spent your entire life inside it, the way you don't hear the hum of a refrigerator in a room you've always occupied. But it is there, constant, directed upward, measurable, Newton would say the floor pushes up, gravity pulls down, the two forces balance, and you stay still. Gravity in this picture is a force, real, directed, proportional to mass, acting instantaneously across any distance. An apple falls because Earth pulls it. The moon orbits because Earth pulls it. The sun holds the planets in their paths because it pulls them across 150 million kilometers of empty space, with no mechanism specified and no medium required. Newton himself found this troubling. Action at a distance, with nothing in between doing the acting. He called it absurd as a philosopher, while accepting it as a physicist because the mathematics worked. Einstein found it untenable, not aesthetically, physically. If special relativity had established anything, it had established that nothing propagates instantaneously. Influences travel at or below the speed of light. A force that acts across space without travel time, without a mediating field, without any mechanism whatsoever, that couldn't survive the framework that 1905 had built. Something had to change. What changed was the definition of gravity itself. General relativity, completed in 1915 after roughly a decade of work that Einstein described as the most grueling of his life, reconceives gravity not as a force but as the geometry of space-time in the presence of mass and energy. Mass curves space-time. The curvature of space-time determines how objects move through it. What we call gravitational attraction is not two objects pulling on each other across a gap. It is each object following the straightest available path through a geometry that has been shaped by the other's presence. The straightest available path. That phrase carries more weight than it might seem to. In flat space-time, far from any mass, the straightest path between two events is a straight line, and an object following it moves in a straight line at constant speed. No force required. In curved space-time near a mass, the straightest available path bends. Not because something is pulling on the object, because the geometry itself is curved, and the straightest line through a curved geometry is not straight in the Euclidean sense. An object following that path appears, from the outside, to accelerate toward the mass. We call it falling. It is, in the language of general relativity, coasting, following a geodesic, the four-dimensional equivalent of a straight line, through a geometry that mass has shaped. The floor is pushing up against you because you're not in freefall. You're being prevented from following your geodesic. The acceleration you feel is not gravitational. It is the floor's upward push, stopping you from coasting through curved space-time the way you would if it weren't there. Astronauts in orbit feel weightless, not because gravity isn't present, but because they are following their geodesic freely, falling around the Earth without anything interrupting the fall. Weightlessness is the natural state. Standing on a floor is the intervention. This is the picture that replaced Newton's. There is an analogy that appears in almost every explanation of general relativity because it is genuinely useful and genuinely limited in approximately equal measure. A heavy ball placed on a stretched rubber sheet creates a depression, a curve in the surface. A smaller ball rolled nearby curves toward the depression, following the shape of the sheet rather than travelling in a straight line across it. The analogy captures the basic idea. Mass creates curvature, curvature influences motion, but it smuggles in a problem. The balls roll toward the depression because of gravity pulling them down onto the sheet. The analogy uses gravity to explain gravity. It is a picture of the effect, not the mechanism. The actual mechanism operates in 4 dimensions, not 2, and the curvature is in space-time rather than in a surface embedded in space. The sheet is a teaching tool, useful for a first impression, insufficient for the second. What general relativity actually says is that the geometry of space-time is not fixed, it responds to the matter and energy distributed through it, and that response is gravity. The two-way relationship is written into the Einstein field equations. Matter tells space-time how to curve, space-time tells matter how to move. Neither side of that sentence is static. Neither side is the stage for the other. They are coupled. Each shapes the other. Newton's gravity was a force cast across a fixed stage. Einstein's gravity is the shape of the stage itself. The floor is still pressing against the soles of your feet. That hasn't changed. What has changed is what that pressure means. Not balance, not equilibrium between two forces, but an interruption. A surface preventing a fall that space-time left to itself would allow. Imagine a box, sealed, no windows, no instruments that can reach outside, no way of observing anything beyond the walls. You're inside it, and you feel weight. Your feet press against the floor. Your body has a downward orientation. If you drop something, it falls. Now the question, are you sitting on the surface of a planet held down by gravity, or are you in deep space, far from any mass, and the box is accelerating upward at exactly 9.8 meters per second squared? You cannot tell. Not because the instruments are insufficient, not because the experiment needs more time, because there is no experiment conducted locally, meaning inside the box, without reference to anything outside it, that distinguishes between the two situations. They are physically identical. Every measurement you make, every sensation your body reports, every result any conceivable test produces will be the same in both cases. This is the equivalence principle. Gravity and acceleration are locally indistinguishable. Einstein called it the happiest thought of his life, which is either charming or slightly alarming, depending on your perspective, because what it implies, followed carefully, is that space-time cannot be flat in the presence of mass. The path from that sealed box to the curvature of space-time is a chain of logic, and each link in it holds. Start with the accelerating box. You're inside, accelerating upward. Someone outside, not accelerating, just floating, shines a beam of light through a small hole in the side wall. By the time the light crosses the box has moved upward. The light beam, from your perspective inside the box, has curved downward. It entered at one height and arrived at the opposite wall slightly lower. The beam bent. This is not controversial. In an accelerating reference frame, light curves. The mathematics of it is straightforward and the physical picture is clear. The box moved while the light was crossing it. Now apply the equivalence principle. If the accelerating box and the box sitting in a gravitational field are physically indistinguishable, if every measurement inside gives the same result, then light must also curve inside the gravitational box. A beam of light crossing a room on the surface of a planet must bend downward toward the mass by exactly the same amount as it would bend in the equivalent accelerating frame. But here is where the chain tightens. Light travels at a fixed speed. Its path through space is determined by the geometry of space. If light curves in the presence of gravity, not because a force is deflecting it, but because gravity and acceleration are equivalent and light curves under acceleration, then the geometry of space itself must be curved near a mass. The bending is not something happening to the light. The bending is the shape of the space the light is moving through. The word locally in the equivalence principle is doing important work, and it is easy to slide past it. Locally means in a small enough region, over a short enough time, in a region where the gravitational field is approximately uniform. Expand the box and the equivalence breaks down. Tidal effects, the slight difference in gravitational pull at different distances from a mass, have no equivalent in uniform acceleration. They are the signature of real curvature, not mere acceleration. A sufficiently large box or a sufficiently sensitive instrument can distinguish gravity from acceleration after all. But locally, and locally is where the physics lives, where measurements are made, where observers exist, the equivalence holds completely. And holding completely locally is enough. It was enough for Einstein to conclude that gravity must be geometry, that space-time must respond to mass by curving, that the curvature must be the thing we have been calling gravity all along. The chain from the sealed box to the full machinery of general relativity is long, and most of it is mathematics. But the seed of it is physical. A body in a box, unable to tell up from acceleration. A beam of light bending because the box moved. The same bend required in a gravitational field by logical necessity. The box is still sealed. You're still inside it. The floor still presses against your feet in a way that tells you nothing by itself about what is producing the pressure. That ambiguity is not a limitation of measurement, it is a feature of the universe. May 29th, 1919. 2 expeditions, one to Sobral in northern Brazil, one to the island of Príncipe off the west coast of Africa, both positioned deliberately, months in advance, for a single event. A total solar eclipse that would last roughly 6 minutes and would, if the weather held and the equipment worked and the mathematics was right, either confirm or refute a theory that had been sitting unverified for 4 years. Arthur Eddington led the Príncipe expedition. He was 36, a Quaker who'd spent the war years in Cambridge partly because his pacifism had kept him from conscription and partly because there was physics to do. The eclipse was, in a sense, his chance, not personally but for the question. General relativity predicted that light passing close to the sun would deflect by a specific angle, 1.75 arcseconds, due to the curvature of spacetime near the solar mass. Newton's gravity, applied to light treated as a particle with mass, predicted roughly half that. The difference was small enough to require the sun's disk to be blocked and the eclipse, so that stars near its edge could be photographed and their apparent positions compared to their known positions when the sun was absent. Príncipe was cloudy that morning. Eddington spent the eclipse watching gaps in the overcast, exposing plates when the sky allowed, not knowing until development whether anything usable had been captured. Some plates were ruined. A handful were not. The results, announced in November 1919 at a joint meeting of the Royal Society and the Royal Astronomical Society in London, confirmed Einstein's prediction. The stars near the solar limb had shifted, not by the Newtonian amount, by the relativistic amount, 1.75 arcseconds, within measurement uncertainty. Space-time curved near the sun, and light had followed that curvature, and the photographs showed it. The room in London received the announcement quietly, then not quietly. The Times ran the headline the following day. Einstein became, almost overnight, a name that existed outside physics, a cultural fact, a shorthand for a kind of thinking that had changed something fundamental about the universe's description. Whether the public fully understood what had been confirmed is another matter. But the photographs existed. The measurement existed. Now, what had actually been measured? Light bending near the sun is often described as gravity pulling on the light, which is a natural description, and also, in the framework of general relativity, slightly wrong. Light has no mass in the rest-mass sense. It cannot be pulled by a force in the Newtonian way. What it does is follow the straightest available path through whatever geometry it finds itself in. Near the sun, that geometry is curved and space-time is not flat there, and the curvature is significant enough at close enough approach to produce a measurable deflection in the path of anything travelling through it. The light isn't being bent. The space it is moving through is bent. The distinction matters, not because one sounds more dramatic than the other, but because one is correct and the other imports a Newtonian concept, force acting on a particle, into a framework that has specifically replaced that concept with geometry. Light follows geodesics. Near mass, geodesics curve. The photograph shows the curve. A century later, gravitational lensing is routine, not in the sense of being unremarkable, in the sense of being a standard observational tool. When light from a distant galaxy passes near an intervening mass, another galaxy, a galaxy cluster, the geometry around that mass focuses, distorts, sometimes multiplies the image. Astronomers find arcs, rings, multiple images of the same source arranged symmetrically around the lensing mass. They use these distortions to map the distribution of mass in galaxy clusters, including mass that emits no light at all. Dark matter, invisible by definition, reveals itself through its effect on the space-time geometry around it, which reveals itself through the paths of light passing through. Eddington's 6 minutes of useful eclipse and a handful of glass plates developed on a cloudy island open something that is not closed. The physics behind it is the same physics. The curvature is the same curvature. The light is still following the only path available to it. The geometry near anything massive enough is never quite flat, and light travelling faithfully along whatever geometry it finds will always show you that. Drop a stone into still water. Watch the ripples. They expand outward from the point of impact at a fixed speed, the speed of waves in that medium governed by its physical properties. The ripple reaches the near bank before the far bank. It reaches the lily pad before the reeds on the other side. Some things get touched by the disturbance. Some things far enough away don't. Not yet, or not at all if the wave dissipates first. There is a boundary. Not a sharp wall, not something you could mark with paint, but a real limit, the leading edge of what the disturbance can reach. Inside that edge, the stone's impact has made itself felt. Outside it, as far as that particular stone at that particular moment is concerned, nothing has changed. Space-time has something like this, more precise, more absolute, and with no dissipation. Every event, every point in the four-dimensional structure, every where and when, sits at the centre of what physicists call a light cone. The name comes from the shape it makes in space-time diagrams. If you draw time running vertically, and one spatial dimension running horizontally, and you trace the paths that light would take outward from a given event in all directions, and also backward through time toward all the things that could have sent light to that event, you get two cones meeting at their tips. The event is the tip. The upper cone opens into the future. The lower cone opens into the past. Everything inside the future cone is reachable from the event by something travelling at or below light speed. A signal sent from the event, a particle that leaves at that moment, a chain of causes. Any of these can arrive anywhere inside the future cone. These are the events the original event can influence. Everything inside the past cone could have influenced the original event. A signal sent from anywhere in the past cone at any time would have had enough time to travel to this event at or below light speed. These are the events that could be causes of this one. Everything outside both cones, the region that opens sideways, neither future nor past, is called the elsewhere, and the elsewhere is causally disconnected. Not distant in the sense of being hard to reach, disconnected in the sense that no signal, no influence, no causal chain of any kind can link the event at the tip to any event in the elsewhere. Not at light speed, not at any speed below it. The geometry forbids it, not as a rule imposed from outside, but as a structural feature of what space-time is. This is what makes the elsewhere strange, the events sitting in your elsewhere right now, things happening on the far side of the galaxy at this moment, things happening in distant galaxies, are not merely unreachable, they are causally outside your universe, in a specific and permanent sense. Nothing that is happening there can affect you yet. Nothing you do now can affect them yet. The influence, when it eventually propagates, will take years or millennia to cross the gap. The light cone is not a metaphor for causality. It is causality, given a geometric form. In flat space-time, and far from any mass, the cones are uniform. Every event has the same cone shape, the same opening angle, the same relationship between future, past, and elsewhere. The speed of light is the same everywhere, so the boundary of causal reach expands at the same rate everywhere. Near a mass, where space-time curves, the cones tilt, not randomly, according to the local geometry, which is shaped by the distribution of mass and energy nearby. Near a black hole's event horizon, the cones tilt so severely that the entire future cone, every possible path forward through space-time, points inward, toward the singularity. There is no future-directed path that leads out. The causal structure of space-time has been arranged by the geometry of extreme curvature so that outward is not a direction any future can take. The event horizon is not a wall. It is a region where the light cones have tilted past the point of no return. Causality, in this picture, is not a law that the universe obeys. It is not an external constraint applied to events from somewhere outside. It is the shape of the light cones, everywhere, at all times. The reason the future cannot affect the past, the reason cause must precede effect, the reason information cannot travel faster than light. These are all of the same fact, stated different ways. The geometry of space-time makes them so. Drop a stone, watch the ripples. The boundary of what they can reach is not a rule about water. It is a fact about what that particular disturbance moving at that particular speed can touch. The light cone is the same fact, larger, permanent, written into the universe's structure at every point for every event, without exception. Whether that counts as an explanation of causality or simply a more precise description of it, I'm not entirely sure the distinction matters as much as it might seem to. A black hole is not, first of all, a thing you can see, not directly. What you can see, what any telescope pointed at the right region of sky will eventually show, is the behaviour of everything around it. Gas spiralling inward, heated to temperatures that produce X-rays. Stars moving in tight, fast orbits around something their paths imply, but that emits nothing. The object itself is defined by an absence, by what it withholds. At the centre of that absence is a surface, not a physical surface, no, not a membrane or a shell or any material thing you could touch or photograph. A boundary in space-time defined entirely by a property of the geometry. This is the event horizon, and its definition is precise. It is the surface at which the escape velocity equals the speed of light. Escape velocity is the speed an object needs to leave a gravitational well without further propulsion. From Earth's surface, it is roughly 11 kilometers per second. Add mass to Earth, compress it, increase the curvature of the space-time around it, and the escape velocity climbs. Compress enough mass into a small enough volume, the Schwarzschild radius, named for Carl Schwarzschild, who derived the solution in 1916, sitting in a trench on the Eastern Front, and the escape velocity reaches light speed. At that surface, nothing that travels at or below the speed of light can leave, including light itself. The event horizon is where space-time geometry has curved to the point that outward is no longer a direction the future can take. From a safe distance, far enough away that the curvature is manageable, consider watching something fall toward this horizon. A clock, say, with a light attached. As it falls, it sends signals back to you at regular intervals. At first, the signals arrive normally, the clock ticking at a familiar rate. But as the clock approaches the horizon, two things happen, both caused by the same geometry, both measurable from your distant position. The light from the clock shifts. It redshifts, stretches toward longer wavelengths, toward red and then infrared, and then wavelengths no optical telescope can detect. This is gravitational redshift, the same effect that general relativity predicts for any photon climbing out of a gravitational well, now taken to its extreme. The photons that leave the vicinity of the horizon have to climb out of the deepest curvature they will ever encounter, and they lose almost all their energy doing it, and the clock slows. From your vantage, the ticks arrive further and further apart. The clock appears to run slower and slower as it nears the horizon, the gravitational time dilation stretching each interval between ticks to longer and longer durations as the geometry deepens. Theoretically and in the mathematics, which is clean even when the physics is strange, the clock asymptotically approaches stopped. It never quite reaches the horizon in your time. It appears to freeze there, dimming, reddening, slowing to something that is functionally motionless and invisible. The infalling clock, of course, experiences none of this. In its own frame, it is ticking normally, falling freely, following its geodesic through space-time. For the clock, the horizon is not a dramatic threshold. Nothing locally distinguishes it. The geometry at the horizon of a sufficiently massive black hole is not extreme. A person falling through it would notice nothing unusual at the moment of crossing. It is only in the global structure of space-time, in the arrangement of light cones, in the fact that all future-directed paths now point inward, that the crossing is irreversible. This asymmetry is one of the stranger features of the horizon. From outside, the infalling object appears to freeze. From inside, if inside is even a meaningful word here, and it becomes less clear the more carefully you think about it, the object crosses and continues toward a region of space-time that the outside observer can never receive information about. Two descriptions, same event, neither wrong. The horizon is not a wall. Walls can be approached from both sides. The horizon exists in one direction only. You can fall toward it and through it, but nothing on the other side can send information back. Not because the information is blocked, because the geometry arranges all future directed paths away from the outside. The light cones, past the horizon, point only inward. What mass has done to time near enough and concentrated enough is this. It has arranged space-time such that one side of a surface and the other side are causally severed. Not by distance, by geometry. The clock keeps falling. From your position, it has nearly stopped. It will appear to hang there almost motionless for as long as you watch. Just below the horizon, something is happening that you will never be able to verify. Cross the horizon. Not physically, stay where you are, stay comfortable, but follow the mathematics across it, and something happens to the coordinates of space-time that is strange enough to sit with slowly. Outside a black hole, in the ordinary space-time around it, the radial direction, the direction pointing toward or away from the center, is spatial. You can move along it in either direction. You can hover at a fixed radial distance, spending as much time as you like at that position, expending fuel to hold station. The radial coordinate behaves like a place, like a position in space you can occupy, leave, return to. Time runs forward regardless of where you are along it. Inside the event horizon, this changes. The mathematics of the Schwarzschild solution, the simplest description of space-time around a non-rotating black hole, derived a century ago and still the foundation of how physicists think about black hole interiors, tells you something specific about what happens to the coordinates past the horizon. The radial direction, the direction toward the singularity, becomes time-like. Not metaphorically. In the precise technical sense, the coordinate that pointed toward the center, which outside the horizon behaved like space, inside the horizon behaves like time. Take a moment with that. Time has a direction. You cannot move backward through it, cannot hover at a moment, cannot choose to return to an earlier position along it. Time is not a place you occupy, it is a direction you move through, inevitably, whether you choose to or not. Tomorrow is not somewhere you can decide not to go, it is simply where you are going, because that is the nature of the time-like direction. It flows. It does not offer alternatives. Inside the event horizon, the singularity occupies that direction, not as a place in space ahead of you, as a moment in your future. The singularity is not a location you are approaching through space, it is a time you are approaching through time. Unavoidable, not because a wall blocks every escape route, but because every escape route, every path through space-time that is directed toward the future, leads there. The geometry has been arranged by the extreme curvature inside the horizon, so that the singularity is forward in time for everything inside. There is no path around it, not because the paths are blocked, because forward is the only direction time moves and forward points there. This is the coordinate swap, space becoming time, a direction that outside the horizon offered choice. You could go toward the center or away from it, becoming inside the horizon something that offers none. The singularity is not a destination you can avoid by steering around it. It is tomorrow, and the day after tomorrow, and the day after that, compressed into a finite proper time that depends on the black hole's mass, but that cannot be extended by any maneuver, any acceleration, any conceivable path. An infalling observer crossing the horizon feels nothing dramatic at the moment of crossing. The local geometry is not extreme, d'abord. For a black hole massive enough, the curvature at the horizon is actually quite gentle, and nothing physically signals the boundary. But the causal structure has shifted irrevocably. The light cones have tilted past vertical. Every future-directed path now curves toward the singularity. the way every future-directed path outside the horizon curves toward increasing time. What the infalling observer has lost is not freedom of spatial motion. They can still move, still change direction, still experience space as three-dimensional. What they have lost is the spatial nature of one of those dimensions. The inward direction is no longer a place, it is a when. The singularity itself, reached after a finite proper time that varies with the black hole's mass, potentially seconds for a stellar mass black hole, potentially hours for a supermassive one, is not a wall and not a place and not a thing that can be photographed or described by any observer who reaches it. It is the point where the equations of general relativity produce outputs that are not physical, infinite curvature, infinite density, numbers that the mathematics generates and that physics cannot interpret. General relativity, which has described everything leading up to this moment with extraordinary precision, the orbit of Mercury, the bending of light, the ticking of GPS clocks, the ripple of gravitational waves, arrives at the singularity and stops predicting. Not because the prediction is difficult, because the framework itself breaks down. The smooth, continuous space-time that general relativity requires ceases to be smooth or continuous. Something is happening that the theory cannot describe, because the theory was built for a regime that does not include this one. What is actually there, at the singularity, is unknown. It is the boundary of what current physics can say. Some theories of quantum gravity suggest the singularity is an artifact, that a complete theory would smooth it out, replace the infinite curvature with something finite and strange but physical. Others suggest it is real, that space-time genuinely ends there. Nobody knows. The equations stop, and past the equations, there is only silence. What we have is this: a region of space-time where a direction that outside behaved like space, inside behaves like time, where the future is not a direction you can choose but one you are already moving toward, where the ordinary geometry of choice and position and reversible motion has been replaced by something with only one direction and no alternatives. Space becoming time, not a metaphor for constraint, an actual geometric coordinate level exchange. The singularity is ahead, not in space, in time. 1.3 billion years ago, in a region of space that had no particular name because nothing capable of naming things existed yet anywhere near it, two black holes finished a long process of spiraling toward each other and merged. The merger took a fraction of a second at the end, the final in spiral, the collision, the ring down as the resulting black hole settled into its final shape. In that fraction of a second, a quantity of energy equivalent to roughly 3 solar masses was radiated outward. Not as light, not as heat. As a disturbance in space-time itself, propagating outward in all directions at the speed of light. The wave moved through space for 1.3 billion years, through the formation of the solar system, through the emergence of single-celled life on Earth, through the Cambrian explosion, the extinction events, the slow accumulation of something that would eventually be capable of building instruments precise enough to notice what was coming. On September the 14th, 2015, at 5:51 in the morning Eastern Time, the wave arrived. It passed through the LIGO detector in Livingston, Louisiana first, a facility consisting of 2 perpendicular arms, each 4 kilometers long, through which laser light bounces between mirrors suspended from vibration-dampened mounts. 7 milliseconds later, it reached the twin detector in Hanford, Washington. The signal lasted less than a second at each site. In that time, the wave stretched one arm of each detector and compressed the other. Not by much, not by anything a human body could feel or any ordinary instrument detect. The displacement was on the order of 1,000th the diameter of a proton. The mirrors moved by less than the width of an atomic nucleus. The instruments caught it anyway. Gravitational waves are not vibrations moving through space. That framing gets the physics slightly wrong in a way that matters. They are vibrations of space itself, oscillations in the metric of space-time, in the fabric that determines what distances and durations mean. When a gravitational wave passes through a region, the region itself stretches in one direction and compresses in the perpendicular direction, and then reverses again at the frequency of the wave. Everything in the region participates. The space between the mirrors themselves, the length of the laser path. What the interferometer measures is the difference in length between its two arms as the wave passes, because the wave stretches one and compresses the other simultaneously. The signal recorded on September 14, 2015, designated GW150914, the date compressed into a label, matched, with extraordinary precision, the waveform that general relativity predicts for the merger of two black holes with masses of approximately 29 and 36 times that of the Sun. The chirp, as physicists call it, the signal's characteristic rise in frequency and amplitude as the objects spiral closer and faster before merger, was exactly the shape the equations had been generating for decades of theoretical work, waiting for data to compare it to. The data arrived at 5:51 in the morning in a quiet building in Louisiana, to instruments that had been running for days and would have looked, to a non-specialist glancing at a readout, like any other stretch of data. Here is the thing worth pausing on, and I want to be careful not to overstate it, because overstatement tends to make things feel further away rather than closer. Before September 14th, 2015, gravitational waves were a prediction, a very well-supported prediction, a prediction that indirect evidence from binary pulsar timing had already strongly supported, a prediction that essentially every physicist working in the field believed to be correct. But a prediction, a consequence of a mathematical framework that describes space-time as a dynamic, deformable physical entity. After that morning, space-time was something that had moved a mirror. The distinction is not philosophical. Instruments had felt something. Instruments that measure distances, the most concrete measurement physics knows how to make, had registered a change produced by the passage of a wave in the geometry of the universe itself. The abstraction had become mechanical. The mathematics had produced a deflection in a mirror that human beings had designed and built and suspended from wires in a concrete building in Louisiana. Two black holes, 1.3 billion years, 3 solar masses of energy, a displacement smaller than a proton. A Tuesday morning that recorded all of it. The universe had been dynamic all along, curved, rippling, responsive to the matter moving through it. General relativity had said so since 1915. But saying so and measuring so are different things, and on September 14, 2015, physics crossed from one to the other. Space-time moved. The instruments noticed. That is, as far as physics goes, enough. Pick up an old photograph. Not scroll past one, actually hold one, the physical kind if you have access to such a thing. Look at the people in it. They are doing something specific at a specific moment in a specific light. That moment is finished. The people may have changed or moved or died. The thing the photograph shows is not happening now, but it happened, completely, with the full weight of a real event, a real arrangement of matter, a real set of simultaneous experiences for everyone present. The past is not nothing. It was something entirely, and whatever it was that with the same thoroughness that right now is this. The question that the block universe poses, quietly, without drama, is whether the past still is that, not was, is. This is eternalism. The view that all events in space-time, past, present, and future, exist equally as fixed coordinates in a four-dimensional structure that does not change, does not flow, does not have a preferred moment called now. The universe in this picture is not a process. It is a thing, a static, complete, four-dimensional object in which every moment is as real as every other moment, the way every point in space is as real as every other point. If time is genuinely a dimension, and the preceding chapters have built a long case that it is, that space-time is a unified geometric structure and not a stage with a clock running beside it, then the logic of the block follows from the geometry almost directly. Points in space do not become real when you reach them and cease to be real when you leave. New York exists right now whether or not you are standing in it. The existence of a spatial location does not depend on anyone's presence or attention. If time is a dimension with the same ontological status, then points in time do not become real as you pass through them and cease to be real as you leave. Last Tuesday exists, not in the sense that it is happening, but in the sense that it is a real coordinate in a real structure, as fixed and present in the geometry as any point in space. The past still is, just as New York still is when you're not there. Most physicists pressed on the question end up somewhere near this view, not enthusiastically necessarily. It is not a comfortable position for creatures whose entire experience is of a moving present, but because the alternative has a problem that is difficult to resolve. Presentism, the intuitive view, says that only the present moment is real. The past is gone. The future does not yet exist. Only now. The problem is, whose now? Simultaneity, as earlier chapters established, is frame-dependent. Two observers in relative motion have different sets of events they would call simultaneous with this moment, different presents, different nows, slicing the four-dimensional block at different angles. If only the present is real, and two observers have different presents, then reality itself becomes observer-dependent in a way that is very hard to make coherent. What is real for one observer would be unreal for another. The past for one observer would be the present for another. Presentism wants a universal now. Relativity does not provide one. The two are in tension, and the tension has no obvious resolution that preserves both. Eternalism sidesteps this by removing the ontological special status of any particular moment. Every point in the block is equally real. The now that any particular observer experiences is real. But so is every other now, everywhere, at every time. The observer's present is not a boundary between real and unreal. It is simply a location in the block, a position on a world line, no more special geometrically than any other position. The past still exists, not as memory, not as record, not as trace, as a region of space-time with the same geometric standing as the present. The coffee cup you held this morning in the specific configuration it occupied at a specific moment, that event is a fixed coordinate in the block. It has not been erased. It is simply elsewhere in the four-dimensional structure, at a location you can no longer reach from where you are now. The photograph shows a moment that, in the block universe, is not gone. It is there, at its coordinates, as complete and real as this one. Whether that is comforting or not depends probably on which moments you are thinking about. I find myself not quite able to decide. The geometry says the past is real. The experience of having left it says something else. Both of those things are true at the same time, which is either a contradiction or a feature of what it is to be a consciousness moving through a block that does not move. The photograph stays the same. You are the thing that changes. The block universe, introduced in the previous chapter, is a four-dimensional structure in which all events exist equally. Past, present, future, each fixed at its coordinates, none more real than any other. It is a picture of the universe as a completed object rather than an unfolding process, and it raises, fairly immediately, a question that the geometry of space-time is very specific about answering. If all moments in the block are equally real, which slice through the block is now? The answer is that every observer has their own, and the slices don't align. Think of the block as a loaf of bread, dense, complete, every part of it equally present in the loaf regardless of which slice you cut. Different cuts at different angles produce different cross-sections. The bread is the same, the slices are different, depending on how the knife goes in. No single cut is the correct cut. The loaf doesn't have a preferred angle. This is roughly the situation with the space-time block and simultaneity, though the analogy strains quickly and is worth letting go of once it has done its work. An observer moving through space-time at a given velocity slices the block along a particular angle. Their surface of simultaneity, the set of all events they would call happening right now, A different observer, moving at a different velocity, slices the block at a different angle. The slices intersect. They share the event of the observers passing each other, but they extend in different directions through the block, picking out different sets of distant events as simultaneous with that shared moment. What is in one observer's present is in another observer's past or future. Not because of signal delay, not because information travels slowly, but because the geometry of space-time distributes what counts as simultaneous differently for differently moving observers. This was established in the chapter on simultaneity, but its implications for the block universe run deeper than the thought experiment alone conveys. Consider two observers passing each other. The moment of their passing is a shared event. Both place it in their present. But observer A's surface of simultaneity, extending outward from that moment, picks up a set of distant events as happening right now. Observer B's surface, tilted by their relative velocity, picks up a different set. At moderate speeds, the difference is negligible for nearby events and grows with distance. At significant fractions of light speed, the disagreement about what is happening right now on the other side of the galaxy becomes substantial, potentially spanning millions of years of galactic history. There is no third observer whose slice is correct. There is no God's eye view that settles which set of distant events is actually simultaneous with the moment of passing. The block contains all the events. The slicing is done by observers, and each observer's slice is as valid as any other. This is what it means to say the block universe has no universal now, that now doesn't exist, or every observer has a now, a surface of simultaneity they carry with them through the block, but now is local. It belongs to a world line, not to the universe. The universe doesn't have a present tense, individual observers do. The absence of a universal now is sometimes framed as a problem, as though the block universe is missing something, as though a complete description of reality should include a global present. But this framing gets it backwards. The block universe doesn't have a universal now because the physics doesn't require one. The physics works perfectly, precisely, predictively, completely, without any reference to a global present. The universe doesn't use a universal now to organize itself. Only observers use nows, and they use their own. What this means practically is something like this. Right now, you're now, the surface of simultaneity you carry at whatever velocity you're moving. There are distant events in the universe that are simultaneously happening according to your slice of the block. You cannot see them yet. The light hasn't arrived. But geometrically they are in your present. They are part of your slice. Someone moving past you at a significant fraction of light speed carries a different slice. Their present contains different distant events. Neither of you is wrong. You're simply cutting the loaf at different angles. The block holds all of it. Every event, every slice, every observer's now, all equally fixed in the geometry. The disagreement about which distant events are simultaneous is not a flaw in the structure. It is the structure working exactly as it should. The crowd in the room is full of slightly different nows. The universe is full of vastly different ones. None of them is the one. Zoom into a photograph far enough and the image dissolves. What looked smooth, a gradient of colour, a continuous surface, breaks into pixels. Discrete squares of flat colour, each one a unit, each one a boundary. The smoothness was never there in the underlying structure. It was an emergent property of looking from far enough away. Space-time looks smooth from where we stand. From any distance at which human instruments have ever operated, the geometry of space-time behaves like a continuous, differentiable surface, the kind that calculus can work with, the kind that general relativity assumes, the kind that produces the precise predictions that GPS and gravitational waves and muon lifetimes all confirm. The smoothness is real at those scales. Nobody is disputing it. The question is what happens when you zoom in far enough. The Planck length is approximately 1.62 times 10 to the negative 35 meters. Written out, 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000wwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwwww scale at which current physics can say anything coherent about space-time. Below it, the two frameworks that describe reality at large scales and small scales, general relativity and quantum mechanics, both break down, or rather, they break each other. Neither was designed for this regime, neither produces reliable output there. To understand why, consider what quantum mechanics does to everything it touches. Quantum mechanics introduces irreducible uncertainty into physical quantities. Not uncertainty from measurement error or insufficient precision, fundamental structural uncertainty that is a feature of the universe, not a limitation of instruments. Position and momentum cannot both be precisely defined simultaneously. Energy and time cannot both be precisely defined simultaneously. These uncertainties are real, and they apply to everything, including space-time itself. General relativity treats space-time as a smooth geometric field, the metric, which encodes distances and durations at every point. Apply quantum uncertainty to the metric, as you must if you take both theories seriously at all scales, and the metric begins to fluctuate, not gently. At the Planck scale, the fluctuations become so large that the concept of a smooth geometry stops making sense. The curvature of space-time varies wildly from point to point at that scale, changing faster than any meaningful average can be established. The smooth surface dissolves. John Wheeler described this in 1955 as space-time foam. The image he reached for was the surface of the ocean, smooth when viewed from altitude, but chaotic and churning when examined up close. At the Planck scale, Wheeler suggested, space-time would be a seething, foaming structure of fluctuating geometry, transient wormholes appearing and collapsing, mini black holes flickering in and out of existence, topology changing moment to moment in ways that have no classical equivalent. It is worth being careful here, more careful maybe than the foam metaphor encourages. This is a theoretical inference. Wheeler was not describing something observed or measured. He was reasoning from the known behaviour of quantum fields and the known behaviour of gravity, and noting that their combination, at extreme scales, produces consequences that no experiment has yet reached. The Planck length is roughly 20 orders of magnitude smaller than a proton. No instrument built or conceivably buildable can probe it directly. The foam is a prediction from a combination of two theories that are not fully reconciled with each other, applied to a regime where neither has been tested. That does not make it wrong, it makes it a conjecture, careful, physically motivated, taken seriously by most physicists, working in quantum gravity but not confirmed. The honest position is that the smoothness of space-time has been verified down to scales many orders of magnitude above the Planck length, and below that nobody knows. The Planck time, approximately 5.39 times 10 to the negative 44 seconds, is the temporal equivalent, the smallest duration at which current physics can meaningfully speak about time. Below it, the concept of a moment, a before and after, a sequence. These may not apply in any recognizable form. Time as a smooth ordered flow may be, at that scale, another emergent property, another illusion of distance, like the smoothness of a photograph that dissolves when you zoom in. What is actually there? Whether space-time has a discrete structure, whether the foam is the right picture, whether time and space are fundamental or built from something else entirely and remains open. The theories that attempt to answer it, loop quantum gravity and string theory among others, make different predictions and agree on very little. What they share is the suspicion that the smooth space-time of general relativity is not the bottom of the story. The photograph looks smooth. Zoom in far enough and it won't. Whether space-time works the same way, that question is still being asked. Run a finger across what looks like a smooth surface, a polished stone, a wooden desk worn flat by years of use, the inside of a ceramic bowl. At the scale your finger operates, the surface is continuous, no gaps, no steps, no detectable grain. The smoothness is real. It governs how objects slide across the surface, how light reflects from it, how it feels under pressure. Look at it under a powerful enough microscope and the story changes. The smoothness was always an approximation. Underneath a lattice, atoms arranged in patterns, space between them, structure that the finger scale experience completely hides. The smooth surface did not disappear when the microscope revealed the lattice. It was never fundamental. It was what the lattice looks like from far enough away. Loop quantum gravity begins with the suspicion that space-time is structured the same way. The theory has a specific historical starting point that is worth naming because it sets it apart from other approaches. When physicists try to apply quantum mechanics to gravity in the standard way, treating gravity as a field on a background space-time, the way electromagnetism and the other forces are treated, the mathematics produced infinities that could not be removed. The technique that works for other forces, called renormalization, failed for gravity. The background space-time approach hit a wall. Loop quantum gravity responds to that wall by removing the background space-time entirely. In most physical theories, space-time is the stage, a pre-existing arena in which fields propagate and particles interact. The geometry may curve, as in general relativity, but it is still a continuous backdrop. LQG abandons this. It is background independent. It does not assume that space-time exists as a smooth continuum before the physics begins. Instead, it attempts to build space-time itself from quantum principles to derive the geometry rather than assume it. What emerges from this approach, through a mathematics that is dense enough that describing it accurately in plain language requires some caution, is a picture of spatial geometry in terms of quantum states called spin networks. A spin network is a graph, nodes connected by links, in which the nodes represent quanta of volume and the links represent quanta of area. The geometry of space in LQG is not a smooth field with values at every point. It is this discrete combinatorial structure, and the smooth geometry of general relativity emerges from it only in the large-scale limit, the way the smooth surface emerges from the atomic lattice. Area and volume in this framework are not continuous quantities. They come in minimum values, quanta, below which subdivision is meaningless. The smallest quantum of area is approximately the Planck length squared, roughly 10 to the negative 70 square meters. The smallest quantum of volume is comparably tiny. These are not just the smallest things we can currently measure. They are, if LQG is correct, the smallest things that exist. Area and volume are discrete in the same way that energy levels in an atom are discrete. Not because we chose to describe them that way, but because the underlying theory produces a discrete spectrum. This is what is meant by saying that space-time is granular at the Planck scale. Not that it is made of small, smooth pieces, that the geometric quantities, the measurable properties of space, come in indivisible minimum units, and the smooth, continuous geometry that general relativity works with is an approximation valid far above that scale. The distinction from string theory is worth noting, because the two are often grouped together as quantum gravity approaches, which is accurate but potentially misleading about their character. String theory is not background independent. It describes strings and their interactions on a pre-existing space-time background. The geometry is there before the physics starts, and the theory operates within it. LQG has no such background. The geometry is what the theory is about. Space-time in LQG is not the container. It is the content. Whether this is an advantage depends on what you think the deeper problem is. Some physicists regard background independence as essential. Any theory that assumes a space-time background is, in their view, smuggling in the very thing that needs to be explained. Others regard it as a technical complication, with no particular philosophical necessity. The debate is ongoing and not close to resolution. What LQG currently offers is this. a mathematically consistent framework in which spatial geometry is quantized, in which the smooth space-time of general relativity emerges as an approximation, and in which the Planck scale structure of space is discrete and calculable. What it does not yet offer, and this is a significant gap, is a fully worked out dynamics. The quantum geometry of space has been developed in considerable detail. The corresponding theory of how that geometry evolves in time, the full quantum version of general relativity's field equations, remains incomplete. The lattice is visible. The rules governing how it changes are still being written. Run the finger across the surface again. The smoothness is there, entirely real at that scale. Underneath, if LQG is right, something quite different is holding it up. Hold a credit card at an angle to the light. There is a hologram somewhere on it, a small patch that seems to contain depth, that shifts as you tilt it, that gives the impression of a three-dimensional object encoded in a surface that is physically completely flat. The three-dimensionality is not there in any material sense. It is information, a pattern of interference encoded in the flat surface that, when light hits it correctly, reconstructs the appearance of depth. The image has more dimensions than its substrate. The flat surface carries the three-dimensional structure. The depth is real as an experience, but it is not where it appears to be. In 1997, a physicist named Juan Maldacena published a conjecture that has occupied a significant portion of theoretical physics ever since. It concerns a specific mathematical relationship, a duality, between two very different kinds of theory. On one side, a theory of gravity operating in a particular curved space-time with one spatial dimension more than the boundary surrounding it. On the other side, a quantum field theory with no gravity at all, living on that lower dimensional boundary. The conjecture, known as ADS/CFT, states that these two theories are exactly equivalent. Every physical process that can be described in the bulk, the higher dimensional interior with gravity, has a complete and precise description in the boundary theory and vice versa. The same physics, two completely different descriptions, one with gravity and extra dimensions, one without either. The implications of this, if the conjecture is correct, and it has resisted falsification for nearly 3 decades, accumulating an enormous body of supporting evidence without yet being proven rigorously, are difficult to overstate without overstating them. So the attempt here is to state them carefully. If a theory with gravity in a higher dimensional spacetime is equivalent to a theory without gravity on a lower dimensional boundary, then in some meaningful sense, the gravity and the extra dimension are not fundamental. They're emergent. They arise from the boundary theory the way depth arises from the hologram, real as an experience, present as a structure, but encoded in something that does not itself contain them in an obvious way. Space-time in this picture may not be the foundational substance that physics has been treating it as. It may be something that appears, that emerges, from a quantum system that is, at the level of its own description, operating without space-time in the usual sense. The geometry of the bulk, the curvature that we would call gravity, is encoded in the quantum states of the boundary theory. Change the quantum states and the bulk geometry changes. The geometry is, in a specific technical sense, a consequence of the quantum information. The more precise version of this, and it is worth holding it precisely because the loose version can mislead, is that the spatial geometry of the bulk emerges from the entanglement structure of the boundary quantum states. Entanglement is a quantum relationship between systems, correlations that are stronger than any classical correlation, that cannot be explained by any shared classical information. In ADS/CFT, the degree of entanglement between different regions of the boundary theory corresponds to the geometric connectivity of the corresponding bulk regions. More entanglement, more connected geometry; less entanglement, more separated. In some formulations, the bulk spatial distance between two regions is directly related to the entanglement entropy between their boundary counterparts. space-time geometry, built from quantum entanglement. This is strange enough that I want to slow down and not dress it up. The claim is not that entanglement produces space-time the way a cause produces an effect. The claim is that the mathematical structure of space-time geometry in this duality is the same mathematical structure as the entanglement pattern of the boundary states. They are the same thing, described in two different languages. Whether that means space-time is made of entanglement, or whether it means something more subtle about the relationship between different levels of description, physicists disagree, and the disagreement is honest. What the conjecture does, regardless of interpretation, is place space-time on uncertain ontological ground. If space-time and gravity can be fully described by a theory that contains neither, then space-time and gravity are not obviously more fundamental than, say, pressure and temperature, which are real and measurable but emerge from the statistical behavior of molecules and do not exist at the level of individual molecules at all. The question this series started with, where do space and time actually meet, has been answered in several ways across these chapters. In Minkowski's geometry, in the space-time interval, in the curvature of general relativity, in the coordinate swap inside a black hole. Each answer was real, precise, and physically grounded. The holographic hint suggests the question may have one more layer, that the place where space and time meet may not be the deepest place, that underneath the meeting there may be something else, something quantum, something informational, something that generates space-time the way a hologram generates depth. What that something is, nobody has yet said clearly. The credit card catches the light. The depth appears. It is not where it seems to be. Two instruments, both calibrated, both tested against every available standard, refined over decades, confirmed by experiments conducted across the full range of conditions that human ingenuity has been able to arrange, both producing results that match their respective predictions to a precision that makes most of science look approximate by comparison, both giving different answers about the same underlying thing. This is the situation in physics, not a recent situation. It has been the situation for roughly a century, since the 1920s, when quantum mechanics matured into a form recognizable to modern practitioners. General relativity and quantum mechanics are the two foundational theories of contemporary physics. Between them, they describe everything that has ever been measured, and they are, at a structural level, incompatible. General relativity describes spacetime as a smooth, continuous, deterministic field. Given the distribution of mass and energy at one moment, the Einstein field equations determine the geometry of spacetime at every subsequent moment. No randomness, no uncertainty built into the structure. The geometry evolves according to a differential equation that is, in principle, exact. The smoothness is not an approximation in general relativity. It is the assumption on which the entire mathematical framework rests. Without continuity, the differential geometry doesn't work. Quantum mechanics describes physical systems as probabilistic in a specific and irreducible way that has nothing to do with ignorance or insufficient measurement. The vacuum, empty space, the ground state, is not empty in quantum mechanics. It seethes with fluctuations, with fields that oscillate at every point, with energies that are never precisely zero because precision is forbidden by the uncertainty principle. The quantum vacuum has structure at every scale, including, in principle, the Planck scale. Apply quantum mechanics to the gravitational field, to space-time itself, and the first fluctuations become fluctuations in the metric, in the geometry. The smooth space-time of general relativity becomes, at small enough scales, a wildly fluctuating structure that the smooth framework cannot accommodate. The differential equations break. The geometry loses the continuity it requires. Two theories, each internally consistent, each extraordinarily precise, each producing nonsense when applied simultaneously to the same regime. This is not a matter of one theory being wrong. Both have been tested to levels of precision that are difficult to fully appreciate. The standard model of particle physics, which incorporates quantum mechanics, has produced predictions confirmed to 12 decimal places in some cases, the most precisely verified numbers in the history of science. General relativity predicts the rate of orbital decay in binary pulsars, the bending of light, the frequency shift of gravitational waves, and the predictions match the measurements without detectable deviation. Neither theory has failed an experimental test, they fail each other. The places where both are needed simultaneously are specific. Inside black holes, at the singularity, where the density is infinite, the curvature is infinite, and quantum effects cannot be ignored, because all the energy is compressed into a region of Planck-scale dimensions. At the Big Bang, where the universe began in a state of extreme density and temperature that general relativity traces backward to a singularity but cannot describe, and quantum mechanics needs a spacetime to operate in, but the spacetime is doing something general relativity cannot handle. In both cases, the two theories arrive together and both stop working. What should be there? What the complete theory would say about the singularity, about the first moment, about the quantum nature of spacetime, is not known. It has not been calculated. Not because physicists haven't tried. Decades of work, significant portions of the field's collective effort, have gone into approaches including string theory, loop quantum gravity, causal dynamical triangulations, asymptotic safety, and others. Some of these approaches are mathematically consistent. None has produced a confirmed, experimentally tested prediction that distinguishes it from the others. The honest position, and this is harder to hold than it might sound because there is always pressure in science toward the suggestion that resolution is near, is that the problem is open. Genuinely, deeply open. Not almost solved. Not missing one key insight. Open in the way that suggests the resolution, when it comes, will require rethinking something that currently seems too fundamental to question. What that thing is, nobody has convincingly identified. General relativity works, quantum mechanics works. Put them together and they don't. The two most tested theories in the history of physics are irreconcilable, and the places where both are needed are real places, not hypothetical constructs, not thought experiments, but the interiors of actual black holes and the actual origin of the universe. Two instruments, both calibrated, giving different readings. The thing being measured is still there. We just don't have a third instrument yet. The questions that remain are not the small ones. Physics, across the preceding chapters, has done a great deal. It has shown that space and time are not separate, that they are components of a single four-dimensional structure whose geometry determines what we call gravity, causality, the flow of time, the survival of muons, the accuracy of every navigation device on Earth. It has shown that mass curves space-time, that space-time can ripple, that inside a black hole a spatial direction becomes temporal. It has confirmed these things not through argument alone, but through measurement, through mirrors moved by waves that travelled for 1 billion years, through clocks running at different rates in orbit, through particles that should have decayed and didn't. The structure is real. The geometry is real. The union of space and time that Minkowski announced in 1908, that Einstein formalized in 1915, that a century of experiment has confirmed without a single clean falsification, that is as solid as physics gets. And yet, whether spacetime is fundamental or emergent remains open. The holographic hint from the previous chapter is not a fringe idea. It is taken seriously by a substantial portion of the field. But taken seriously and established are different things. If spacetime is emergent, if the geometry arises from something more fundamental, entanglement, information, some quantum substrate that current theory cannot yet name, then the questions asked in this series about where space and time meet would need to be reframed. Not abandoned, reframed. The meeting point might be deeper than the geometry. What happens at the Planck scale is not known, not approximately known with details to be filled in, genuinely unknown, in the sense that no theory of quantum gravity has produced a confirmed experimental prediction that distinguishes it from the alternatives. Loop quantum gravity, string theory, causal dynamical triangulations. Each offers a picture of Planck-scale structure, and the pictures are different, and none has been tested against nature in a way that settles the question. Whether the block universe is physically real or a mathematical artifact of the formalism is a question that physics and philosophy share, and neither has closed it. The block is consistent with everything measured. So is a universe in which the past exists only as encoded information, rather than as a real geometric region. The equations do not distinguish between these. The experience of being a conscious observer moving through time does not obviously favour one over the other. The question stays open. What a complete theory of quantum gravity would say about time is perhaps the strangest open question of all, because some approaches suggest that time would not appear in the fundamental equations at all, that it would be an emergent quantity arising from the quantum dynamics in a way that produces the experience of temporal flow without time being built into the foundations. The problem of time in quantum gravity is a technical problem and a conceptual one simultaneously, and the technical and conceptual difficulties reinforce each other in ways that have resisted resolution for decades. These are not gaps at the edge of a mostly complete picture. They are gaps near the centre. There is something, though, and this is the thing I keep returning to, the thought that hasn't fully closed since the beginning of this. There is something fitting about the incompleteness. The union of space and time was not a final answer. It was a deeper question, wearing the shape of an answer. Minkowski said that space and time individually were doomed to fade into shadows, and only their union would preserve an independent reality. But the union itself, it turns out, may not be the bottom. The shadows may go deeper. The questions that remain are not failures of the project. They are what the project opened. This has been a long time to spend in one place, sitting with the ideas that resist quick resolution, moving slowly through the geometry of a universe that turns out to be stranger than it appears from the outside. If you stayed through all of it, through Newton's stage and Minkowski's lecture, and the muons and the mirrors, and the coordinate swap inside the horizon, then something of what these questions feel like has, maybe, settled slightly. Thank you to everyone who supports The Sleepy Physicist on Patreon. Because of you, this place exists. If you would like to help keep it going, the link is in the description. The union of space and time, first glimpsed in 1905, is still unfolding. The questions are still open. That's not a problem. That's the work.